Chapter 4. Chapter 4 is about series circuits. We're going to start actually analyzing series circuits. We are going to learn all the different rules and criteria that define a series circuit. But before we start into series circuit, we have to understand what is an electrical circuit. So we discussed earlier what was an electrical circuit, but now we are going to reiterate what it is. And so an electrical circuit has to have a voltage source, a power source. It has to have a load, and it has to have a closed path. So this right here, it is considered an electrical circuit because it has the load, it has the voltage, it has a path, and it has a load. 3 loads actually. In this case represented by 3 resistors. So it is a electrical circuit. So what is a series circuit? A series circuit, or something to be connected in series, is something that only allows one single path for current, which means current can only go through it and that's it. It has no other way to go through it. So like in this case, we have the voltage source, the current goes through this path, it goes across this resistor, it goes across, continues the path, it goes across this resistor, continues the path, goes across the other resistor, continues the path, and goes back to the voltage source. So we have a closed path. We have going from the positive all the way to the negative terminal of the voltage source. Another way we can understand what a series circuit is that resistor components, each component only has a single common terminal. If they have more than a single common connection, then they are not in series. Like in this case, this resistor is only connected to this resistor from this point, but this resistor is not connected to this resistor at a different point. So for something to be series, they can only be connected at a single point. So let's see. This resistor comes here. This is terminal 1. This is terminal 2. So let's check. This is terminal 1. This is terminal 2. So resistor R1 and R2 are only connected at terminal 1. Terminal 2, it is connected to the source. The terminal 2 of the R2, it is connected to R3. So they satisfy that criteria. Now let's check if current has different options, different paths for it to go. The current comes here, it has to go through here. Then it comes here, it has to go through here. Then keeps going. There is no other way. So these resistors are connected in series. It is important to understand that it doesn't matter how it looks, how the circuit looks, as long as we can trace the path and see that they are only single connected, then they are in series. You see, this one is all weird looking and is still resistor connection in series. Then right here we can follow it and we see that it is a single path connected from point A to point B. So it is a series circuit. Now, a series circuit rules for currents. What it is a characteristic of a series circuit, it is that since we have a single pathway for currents, current is going to be the same all across the resistor. So once you have calculated the current supplied by the source, you know the current across resistor R1, you know the current across resistor R2, and you know the current across resistor R3. They are all the same. This is a characteristic of series circuits. We always have the same currents, and that comes down to the fact that current has no other way to go but to stay together in the single path all across the circuit. how do we calculate the total resistance? We have been used to, in chapter 3, to seeing a voltage source and a single resistor. In this case, we have a source and we have 3 different resistors. So how to calculate the equivalent resistor? So in a series circuit, the way we calculate the total resistance of the circuit, it is by just mathematically, algebraically adding them. So we would say 680 ohms plus 1500 ohms plus 2200 ohms. So that's going to give us a total of 4.38 kilo ohms. So in order to find the total resistance of the circuit, we would just add them linearly. How do we find the voltage? How is the voltage divided across the circuit? So let's look at this example. We have a voltage source, Vs represents the voltage source, and then we have the 3 different resistors. So the way we can approach this problem, it is as follows. So we know that the currents across the circuit should be the same. How do I calculate the current? There are 2 ways. One, I can calculate the total current, the total resistance, and with total resistance, I can calculate the I source because I have the total voltage. Or I can calculate the voltage across this resistor, the voltage across that resistor, and the voltage across that resistor. So in a series circuit, it is important to understand that while current it is the same, voltage is not. In voltage, I have a total voltage source, and this voltage is going to get divided across this resistor, that resistor, and that resistor. What do I mean by divided? The voltage is going to get consumed by this resistor, consumed by that resistor, and consumed by this resistor. How? It gets consumed in the way that after it goes through R3, the voltage at this point should be 0. So some of the voltage gets consumed here, some of it gets consumed here, some of it gets consumed here, to the point that when I get here, I have 0 volts. How is the voltage consumed? So we can assume that it is proportional to the value of the resistor. The higher the value of the resistor, the more voltage it consumes. So the lower the value of the resistor, the lower the voltage it is consumed. The higher the voltage, the higher the resistor it is consumed. Okay? So this is important. Then I can say, if I calculate the voltage consumed by R1, we can call V1. The voltage consumed by R2, we can call it V2. And the voltage consumed by R3, we can call that V3. If we are to add V1, V2, and V3, that has to be equals to the voltage source. That is known as the Kirchhoff voltage law. And that's going to come in the next slide. But right here, let's concentrate on this table. How do we tabulate current, resistance, voltage, and power in a series circuit? So if we add up all these, as we did before, we calculated that it was 4.38. So if we divide 4.38, the voltage by that number, we divide 12 volts by 4.38, or 4,380 ohms, we calculate that we have 274 milliamps. But we know that because they are connected in series, the current I1, I2, and I3 is the same as I source. So that's why I add them together to calculate the I source, because I can use the fact that they are in series, so they are the same. Then I have the value of the resistors given to me, I add them, and I get the R total. Now, using Ohm's law, I can find out what is the voltage across this resistor. So voltage is B times, the voltage is R times B. So what you're going to do is you're going to do the current, which is 274 milliamps, multiplied by, you can take that, the 680 to kilo ohms, so you get rid of the millis, and that is going to give you, if you multiply them using Ohm's law, I'm going to get 186 volts. According to what I said, that should be the lowest voltage. If we multiply 1.5 times 2.75, I get 4.4. This resistor is almost twice that, so I get almost twice the voltage. And then I get 2.2, this should be the highest drop right here. So I get 2.2 times 2.74. The voltage across this resistor, the voltage drop across this resistor is 6.03. If I add them all up, I get 12 volts. And that is exactly what I need. I need to subtract 1.86 here, 4.11 here, 603, so that when I get to this point, it should be 0. For the power I can use BI, since I have the voltage and I have the current. I multiply the voltage times the current, I get this power. I do the same in power, and then it is important to understand the power just as voltage. If I add up individual powers, they should sum up to the P total. How do I calculate the P total? I calculate the P total by multiplying the I total by the V total, and that is my P total. So stop right here.